All right, so in this video, we're going to start off by talking about the idea of eccentricity. And so eccentricity is defined as PF equals EPD, where PF is the distance between point P and foci F, and PD is the point P and directrix D. Now, you'll see up here I have the three different cases we're going to look at: the parabola, the ellipse, and the hyperbola. And one of the things I wanted to point out right off the bat is for the parabola, we've discussed the directrix in probably more detail than you'd care to acknowledge. But for the ellipse and the hyperbola, we haven't. But for the ellipse and hyperbola, both of which actually have two directrices. Now, I'm not going to push that all that hard, but you just need to know they exist for the fact of this idea of eccentricity. So PF is the distance, for example, from here to here. PD would be the distance from the P to D. And in all three of these, I've got everything labeled and everything marked that you'll need. So there's the basic idea of eccentricity. Now, this idea is going to give us a numerical value. The numerical value is going to tell us specifically what type of conic we might be dealing with. So for example, as we know, the definition of a parabola says that this distance here equals this distance here. If that's true, even though my picture might not support it, but by definition, this distance would equal this distance, that would mean the eccentricity E is equal to 1. So for a parabola, the eccentricity is always equal to 1. For the ellipse and the hyperbola, they're not quite as obvious, but with a little bit of investigating, you'll see that 0 is less than E is less than 1 for the ellipse, and then E is bigger than 1 for the hyperbola. Now, the way that it's presented up here is shown basically so that the definition itself can be easily related to the graphs. But when it comes to functionality, I prefer to view eccentricity as C over A. And if you remember, the C value for the ellipse, so for the ellipse, I'll just write this on here. For the ellipse, C equaled the square root of A squared minus B squared. And for the hyperbola, the C equaled the square root of A squared plus B squared. And those come from the secondary formulas. But regardless, I prefer to look at it like this because you'll see the E equaling 1 here just says that C equals A in this particular case. Here, this means that E is a proper fraction, which would mean that the A is bigger than the C, right? The A, the distance from the center to the outside of the ellipse, is bigger than the distance from the center to the foci, which makes sense. And then E being bigger than 1 implies that C is bigger than A. So the foci would be outside of that fundamental rectangle we drew with those vertices for the hyperbola. And so this idea is far easier to remember what the conditions are necessary to be met for each of these conics to exist given their eccentricities. Okay, so now we're going to take a look at conics in polar coordinates. And so what I've drawn up here is just the bare minimum of what we need to get started. This is going to be some coordinate axes, let's say. This is going to be our polar curve, and this is just clearly a part of it. And then our point would be our point r theta in polar coordinates. This would be one of our directrices. We'll say x equals k since it's running horizontal here. And then I've labeled this guy right here as our foci 0, 0. Okay. Now, in order to come up with the equations for these conics in polar coordinates, I'm going to go ahead and construct a triangle. And so my triangle is going to come out of the foci into the point, and then I'll drop down to my perpendicular. We'll call this guy r, and we'll call this guy theta, to no one's surprise. And then we'll also be able to note that the distance from here to here, this would be r cosine theta, r cosine theta. So using your trig functions, you can see that we could solve that thing for the missing part that we need is r cosine theta. I'll also go ahead and mention that the distance from here to here we're going to define as k. Okay, and again, it's nothing special. If we start at 0, 0, and this is x equals k, we can call it whatever we want to call it, but we're just going to say k so that we can get off the ground, and then if we need to make adjustments later, we can. All right, so we also now are ready to remember that PF equals EPD, right? The definition of eccentricity. So from this guy, the PF is going to be P to F, which is going to be R. So I'm going to call that R. Times or equals E times PD. So P to D. This is why we had to define this a little more formally. To figure out what this is, we're going to take the K minus the R cosine theta. So K minus R cosine theta. Now, there's nothing special to what's coming next. I'm just going to do a little bit of algebra. I'll distribute that and get an EK minus ER cosine theta. I'll move the cosine term to the other side. So R plus ER cosine theta equals EK. I'll factor out the R and divide off the rest. So R equals EK over 1 plus E cosine theta. So remember, this is a polar equation, right? R's and thetas, and that's what we have here. The extra E that you're seeing here, that's going to be our eccentricity. So what's going to come into play is a bunch of varieties now of the way this might look. The way that we drew our picture, we so happen to stumble upon a cosine. We so happen to stumble upon a plus, but these could very easily be signs. These could very easily be negatives. And so what I would encourage you to do, and again, this is just one specific general case, I would encourage you guys to take a look at figure 11.53 on page 691. That's going to give you a better understanding as to what the conic will be doing given a possible change from cosine to sine or a possible change from plus to minus. It's a pretty good description they give in that figure. All right, so in this example, all we're going to do is just determine what type of conic this is. And so this was the polar formula I came up with just a moment ago. So all I really need to do is study the eccentricity. Remember, we know that if the eccentricity falls within a certain interval, it's going to be a certain type of conic. So that's what I want to focus in on. One difference in the problem that I've selected versus what we came up with, as you can see after having looked at the figure on page 691, is that we have a minus here versus a plus here, which would only change the major versus minor in terms of the conic and how it is graphed. So for us, what I want to do is I want to get this guy right here to be a 1. All right, so I want there to be a 1 right there. So I'm going to take everything and I'm going to divide by 5. If I divide by 5, that's going to give me a 16 over 5 divided by 1 minus 3/5 cosine theta, which immediately tells us that the eccentricity is going to be 3/5. And with an eccentricity between 0 and 1, that's going to imply that this conic is an ellipse. And that's really all that I care about in this particular example. This looks very unusual if you've never seen it before. It's considering how experienced you probably are with many of the conics. So being able to take something like this, and by simply being able to manipulate it to get this guy a 1, that coefficient out in front of either sine or cosine will always give you the eccentricity. Once you know the eccentricity, then you automatically will know what type of conic it is. And from there, you can study whatever other parts of the conic you care to. But I just wanted to show you a real quick example how all that relates compared to our new form versus our old form.